Lewis structures are our way of drawing a stable structure to try to understand what's going on. It really doesn't matter, but there's certain different ways to draw things, but the main way we think of it is typically one of the Lewis structures. Now, we're going to usually use the chemical formula as a guide. Organic compounds are going to be a beast, but for the most part, we're going to use the chemical formula as a guide. Like, say, if I'm going to do HCN, we'll try PO4 3 minus, and then we'll try NO2. So the first thing you always want to do is count the number of electrons. Count the number of electrons, because we're going to need that. We're going to need the number of electrons when we go through these. So 1, 4, and 5. So 1, 4, 5, that's 9, that's 10 electrons. The second thing we're going to do is we're going to try to put the center atom. The center atom is usually the first non-hydrogen atom. First non-hydrogen atom. And then we'll put single bonds to everything around it. We may have to rearrange the hydrogen if the center atom cannot make enough bonds. So that used 1, 2, 3, 4. We've used up 4 electrons. Now remember, hydrogen only wants 2 electrons. Hydrogen only ever wants 2 electrons. If you make 2 bonds to hydrogen, you're probably wrong. You are probably wrong. So don't try to be making more than 1 bond to hydrogen. Don't put hydrogen in the center and put C on this side and on the other side. You'll be wrong. 9 times out of 10. So we're going to put the remaining electrons around the outer atoms until they have an octet. So 1, 2, 3, 4, 5, 6. Nitrogen now has 8 electrons. So that's step 3. We put the added electrons. If there's any electrons left, we put them on the center. There's no electrons left, so we can't put any on the center. Step 4 is we're going to make double bonds to try to give the center atom an octet, and to try to reduce the formal charge. Remember, a formal charge is when we have more electrons than we should. Nitrogen should have 5. If we count the electrons here, we have 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons around it, and we only expect it to have 5. So it has a high formal charge. Carbon wants an octet, and it only has 1, 2. And it's expected to have 4. So we're going to put double bonds to give octets and reduce the formal charge. So I took 2 of these away to make a double bond, and a second 2 of these away to give it a triple bond, thus giving it carbon an octet. 1, 2, 3, 4, 5, 6, 7, 8. Carbon has an octet. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 as an octet. Carbon has 1, 2, 3, 4. Formal charge of 0. Nitrogen has 1, 2, 3, 4, 5. Formal charge of 0. That is as happy as it can be. Then we'd often look at electronegativity, or is there any resonance structure? A resonance structure is a structure where we can move around double bonds and lone pairs to rearrange the pi bonding. And we'll talk more about pi bonding in a minute. But we can rearrange these guys to make different bond setups and have the same overall shape. But in this case, this one, nothing more can be done. So phosphorus. 5 from phosphorus, 6 from oxygen. 6 times 4 is 24. And then another 3 because it's charged -3. So 24 plus, so 29, 32 electrons. We're going to put a P in the center because it's the first element. That's not hydrogen. Put 4 oxygens around it. That knocks off 8 electrons. We're down to 24 again. Now we're going to put 6 on each because these are the outer atoms. That gives all oxygens an octet. And the phosphorus has an octet. Is that a valid structure? Yes. Is that the only structure? No. Because right now, if I count this, every oxygen has a formal charge of -1. Phosphorus has a formal charge of +1. Now, we expect the total formal charge of the whole structure to be 3-. So we definitely should see at least 3 formal charges. But we see 4 and a +1. So is there another way to draw this to reduce the formal charge? And here's where the resonance structures come in. If I take one lone pair and swap it down, what we have is phosphorus has an expanded octet and it has no formal charge because now it has 1, 2, 3, 4, 5 electrons around it. It has 10 electrons total, but 5 electrons totally around it. And resonance structure allows us to swap these double bonds around. This double bond could go down to there, and so we just simply, this lone pair comes down, makes a double bond, kicks this electrons up. So we could have 3 other resonance structures you could draw. 3 other resonance structures you could draw with that guy. Now, phosphorus has an expanded octet. The rule for expanded octets are that any element row 3 and below, so row 3 going down, can have expanded octets because they have the 3D or 4D or 5D or 6D orbitals that are not filled. So row 3 and below can have greater than 8 electrons. But row 2 cannot. They can only ever have 8 electrons. Now NO2, 5 from nitrogen, 6 from oxygen times 2, so 12, so 17 electrons total. This is going to be a problem. 17 electrons means we're going to have a odd number of electrons, means we're going to probably have a radical. Whenever you have an odd number of electrons, there's a good chance you're going to have a radical. There's no helping it. So putting this on, I've used up 4, so we're down to 13. I'm going to put 12 around the oxygens, and then I have to put 1 lone electron around the nitrogen. However, nitrogen has 1, 2, 3, 4, 5. Well, we cannot achieve an octet with a random electron. We can still get it closer. 5 is not close enough. We could get it to 7 electrons. So what we're going to do is we're going to take away 2, put a double bond. Now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8, and 0 formal charge. This oxygen has a formal charge of -1. This nitrogen has a formal charge of 1, 2, 3, 4, plus 1. The net charge is 0. However, you could also, hypothetically, draw it like this. Put the double bond lone pair there and put the radical on the oxygen. In this case, 1, 2, 3, 4, 5, 6. This has 0 formal charge, this has 0 formal charge, and this has 0 formal charge. There's 2 different ways to draw that with a radical here or the radical there. Either one would be valid. But the idea is there will be a radical because of that. And there should be a double bond. We could switch the resonance structure and put the double bond on the other side in the radical here. Or just swap it over here and put the formal charge there. That's what it means to be a resonance structure. I could redraw this here and still be the same structure. Now, electronegativity. Before we go any further, electronegativity then looks at whether we have a molecular dipole within here. Now, we'll have to get into shape before we can finish talking about electronegativity, but we look at the difference in electronegativity between 2 or more atoms. While there's a hard and fast rule that I like to go that electronegativity difference, so the change in En, when this is greater than 0.4, we say this is polar. Typically, carbon hydrogen is 0.4, so it's nonpolar. But the big thing to look at is if you have these 4 elements, N, O, F, and Cl. N, O, F, and Cl. If you have these elements and they're not adjacent to themselves, so an N and O bond, a P and O bond, a C and N bond, it's not O adjacent to O, it's not N adjacent to N. These can be a polar bond. If it has these molecules and it's not the element next to itself, it can be a polar bond. We'll talk more about whether it's actually polar or not when we get to shape in a minute.